All right, welcome to structural steel design. First, we're going to just talk about steel in general, and then some advantages and disadvantages, and how we designate structural steel shapes. So, what is steel? I hope you covered some of this in your materials class, so that might be a bit of a review. But what is steel, right? If we look at the periodic table, there's no steel element, right? But there is iron, right? Iron makes up about 98% or more of steel. And then you have other stuff. Such as carbon is often one of the things that you add to iron to make steel. And then other alloys like with nickel, manganese, chromium. It's usually carbon and iron are your two big ones. Back in 1855, they perfected the Bessemer process. Right? Bessemer process, which is still used today. You can go to foundries and watch them take melted iron ore and at the other end of the steel mill come out with a steel shape. Or at least some type of shape that then can be used to create your structural steel shape. So if you want to understand the process a little bit more, there's a video that I have linked here. Might be good to watch. You input your iron ore, some limestone, other stuff, blast furnace, get out all those impurities. Eventually it comes down to making steel, then you cast it into different generic shapes, billets, blooms, or slabs, which are then rolled into the actual products that you see making structural steel shapes. So sometimes this is done at different places, maybe not. I went to a steel mill a couple years ago with AISC in Texas in July. It was 120 degrees in the steel mill, and it was 105 degrees outside, so outside felt cool compared to the steel mill. And you have to wear long sleeves, long pants, eyeglasses, all that. So, yeah, if you'd like to watch, I have a video down here. good to familiarize yourself with how they make steel. Okay? So that's how we make steel. Now, if we're talking about the mechanical properties, the material properties of steel, if we look over here, here's a stress strain, right? Over on the left side, the stress strain curve of typical steel, where we have a linear elastic relationship, right? E, that the slope of that line is E. And then after you hit a certain yield stress, you begin to have plastic strain, right? Before you hit yield, if you add a load and you take it off, you are able to recover that deformation. After that yield strain, you're going to have unrecoverable strain, right? If we, let's see, if we load it up to, if we go and we load it up to here, we unload it, it unloads at that same slope. But you have some plastic strain that you can't recover from, permanently deformed. Then you have this plateau where you can't apply any more force, because at the force you're at, it's just going to keep deforming, right? Eventually you can start adding a little bit of load, but it comes over here and eventually fails. Right, we have the plastic strain part, let's see. Deforms with no additional load. And then after that, we do have strain hardening, right? Where your strength will increase, but not the same way as over in the elastic, right? Very different slope there. But it plastically deforms. And eventually it breaks. So you have your elastic portion, your plastic strain, and then your strain hardening section. If you look at over here on the right, different types of steel have different stress strain curves, and you'll see the elastic portion is very, very small compared to the plastic deformation. So what that means is, if we're looking at a football field, and of course I chose Purdue because they're the best. If you start on the 0-yard line, the 1-yard line, right? Start at 0. The 1 yard line is where you hit yield, where you've finished your elastic portion and you've now started plastic deformation. But you don't, right, go. Actual fracture of steel doesn't occur until you hit a touchdown at the other end of the field. So, for those who are my sports people, there's my sports analogy, right? That just tells you how little that elastic portion of steel is. Which could be a good thing. We'll talk about advantages and disadvantages. Why could that be a good thing, right? You may have a lot more warning before fracture happens. It's not like a brittle failure where you have no warning. You have a lot more ductility. But keep in mind how much ductility you have compared to your elastic portion. Right? If I look at that up here, this is my fracture, where those curves end. We talked about the things that are included with your iron, such as carbon. Carbon is a very big thing that you add into steel, or add into iron to make steel. But your carbon content affects your behavior. You can probably tell from this, as we increase carbon, what happens? You may get a little bit stronger, right? My yield strength increases, right? And my ultimate strength, where I fracture, increases. But it fractures with a lot less applied strain, right? So my ductility decreases. So you can include more carbon to increase your strength, but no, you're more likely to have a brittle failure. A failure without too much warning. And so we have different kinds of steels. We have a low carbon steel, which is less than 0.15% carbon. A mild steel, which is structural steel, 0.15 to 0.29%. A medium carbon, 0.3 to 0.59%. And a high carbon steel, you're starting to talk about some cast iron, so 1.7%. Is that a 1? I think so. If you think about it, why don't we make buildings out of cast iron anymore? Because there's too much carbon and they fracture. So, yeah. So we've talked about the material properties, and the effect of carbon on those material properties. How do we determine material properties? I hope you got to do some of this in a materials class. If not, I encourage you to watch the tensile test videos to see how they are performed. But basically, right, you take a dog bone piece of steel, and you apply a force. And you start out with some type of area, and eventually, as you pull it apart, it elongates. So you've applied an extensometer to measure your change in length. It's a delta L, right? If your original length is L. And what can you get from that, right? As long as you're in the elastic range, your stress is your force over area, and your strain is your change in length over length. And ultimately, you can develop a stress strain curve, right? Where you have your elastic range, ultimate, or your yield stress, and then your ultimate. So a tensile test measures stress and strain. You can calculate your elastic modulus and your yield stress, and ultimately your ultimate stress as well. So that is a tensile test. Hopefully you guys have seen one or watched a video of one, I hope, in materials class. If not, the video is right down there. Okay? Actually, I should say elastic stress equals E. Because these are true no matter what. Although your area might decrease as you apply your tensile force due to necking. Another Another test that is often used for material properties is the Sharpie test. And this measures fracture toughness. If you watch the video on how it happens, it's a hammer that swings down. And breaks your specimen. This is one thing to talk about, and I hope you talked about it in your materials class, is the effect of temperature, which kind of makes sense if you think about it. If something's colder, it'll probably behave more brittly, right? Hot. More ductile. You can kind of see right here, right? Cold, brittle, hot, ductile, and then there's a transition. And watch the Sharpie test video to see those more. Yeah, to see this actually in action. If we were in class, I would be showing you these, so please go watch them. Thank you. So why use steel? What are the advantages? We've already talked about some of them. It has a high strength, especially compared to its cost. So it's economical. It's uniform. You know, wood doesn't have a uniform cross section. Concrete could be more uniform, right? It's an aggregate with a paste with cement. Let's see. It does have elasticity compared to, again, thinking about concrete. Concrete doesn't bounce back, right? Steel does, or can, as long as you haven't reached yield. Steel is pretty permanent. It has that ductility to it, especially compared to concrete, right? In tension, which would you rather have holding you up, a concrete beam or a steel beam? Let's see, it's pretty tough. Talking about fracture, it takes a long time for it to get there. And steel is actually very sustainable. You can recycle it. If you tear down a building, take its steel components, melt them back down and make something new, which you can't do for other types of materials. Disadvantages, it doesn't really like water, right? Corrosion. It is susceptible to temperature changes, particularly fire, right? So you need to fireproof it. It is more susceptible to buckling and compression than like concrete would be. and it can have eventually, due to fatigue, right? If you think about a paper clip back and forth, you'll eventually break it. Similarly with steel, if you constantly are putting on loads and taking them off, eventually it'll hit yield and ultimately deform excessively or break. And then it can have a brittle fracture. Down to eventually, right? Especially if you have high carbon content, if it's cold, if it's super cold, right? So steel is the biggest things are it's very economical for its strength. And it has ductility. Those are probably the biggest advantages of steel. You just have to mitigate water and fire. So let's talk about structural steel shapes, right? What happens is I go to my catalog and I say I'd like to order these shapes for my building, right? For my bridge. So what do those shapes mean? Well, if we start over, we're going to start over on this side. The I-beams. We have 4 different designations. The most common being the W. W stands for wide flange. The S is American Standard Beam. HP, the P stands for pile. It's an H pile. Right? It's an I-beam, but if you turn it on its side, it looks like an H. And then the M is a miscellaneous H shape. So that's what those letters stand for. Again, wide flange is what you will likely see most of the time. Now, the numbers after them, what do they mean? Well, let's start with the first one. The 27 means it is 27 inches in nominal depth. That's its overall depth. Right? Nominal depth. Say nominal because it's usually not exactly 27, right? It's like a 2x4 is really like 1.5 by 3.5. So it's nominally 27 inches. And it weighs 114 pounds per linear foot. So if I look at my next one, it has a 12-inch nominal depth, and it weighs 35 pounds per foot. My H pile is probably figured out my pattern here, right? 12 inch nominal depth, 74 pounds per foot. Eight-inch nominal depth, 6.5 pounds per foot. Now, why do they have different weights per foot? If you have thicker flanges, if you have a thicker web, right, those will weigh more. More material, more weight. And steel is sold by its weight. So when we eventually get to designing and it says choose the lightest section or the most economical section, it's because you want the lightest thing. It'll weigh less, it'll use less steel and cost less money. So those are all my H shapes or my I shapes, depending on which way you're looking at them. Now if I look at my next one, I have my channel. That's C for channel, or miscellaneous channel. Both of those follow the same designation as the H or I beams, W shapes, all those, right? 10 inches nominal depth by 30 pounds per foot. This one is 18 inches nominal depth by 58 pounds per foot. Right, and again, I'm talking about this depth right here, this overall depth. HSS stands for hollow steel section. And there's different kinds. There's rectangular and there's also circular. Rectangular or square, and also circular. And this, we actually have something different now. This designation, these numbers mean it is 14 inches in one direction. So let's say long by 10 inches wide by 5/8 inches thick, a wall thickness, right? That's the T. So if we're looking at this, let's see, H would be 14, B would be 10, and T would be 5/8. And again, these are actual nominal. The designation in your book, there's tables in the book that give their actual numbers in your manual. If we look at the L, that means a single angle, right? Because it looks like an L, right? And it is similar. It would have the two sides are called legs, right? So it has a 6-inch leg by a 6-inch leg by a thickness of the legs of a 1/2 inch. So this is a symmetric or an angle with two legs that are the same size. They can be different sizes. If I have a 2 in front of my L, it's now a double angle. And LLBB, there's two different things, LLBB and SLBB. LLBB is long legs back to back. So this is two 8 by 6 by 1 inch angles. So that means it looks like I'm exaggerating, but like that, where the long legs are the 8 inches long. That's why I can't draw 8s like that. Okay, 8 inches long. The sides that aren't together, the short legs back to back, or the short legs that are not back to back, are the 6 inch legs. And the thickness of the angles is 1 inch. If you look in the manual, there's also a different separation that's not given in this designation. So 2L, double angle. The two angles have legs, one leg that's 8 inches, one leg that's 6 inches. The legs are 1 inch thick. Long leg back to back means the two 8 inch legs are back to back. And the 6 inch ones are out to the side. Finally, we have a WT. If you see a T after a W or an S, all the ones that we just did, the W, S, M, not H, but right? WT means I took a W and I cut it in half to make a T. It is half of a W shape. Now it is 18 inches deep by 151 pounds per foot weight. That means what I did was I cut a W36, 18 times 2, by 302, 151 times 2, in half through the stem. So it is literally the same thing, just cut in half. So you cut everything in half. So those are all my different steel shapes and what their letters and numbers mean. Finally, if you look in your steel manual, page 2-48, this is a good one to tab. Highly recommend investing in tabs. I'm going to discuss tab locations. But for now, this is a very good one. This is the materials and their, right? Typical materials or material, typical material for each steel shape and their corresponding material properties. FY and FU. You can see if it's a dark section, dark square, that's the preferred material. So if I look for a W shape, W shapes are typically made out of A992 steel. That have a yield stress, right, Fy, of 50 KSI and an ultimate stress, tensile stress of 65 KSI. If I go look at like the channels or angles, those are typically made out of A36 steel, which has an Fy of 36 KSI and an Fu of 58 to 80. Yeah. Usually when we're doing our examples, we'll use the lower number to be conservative, so we'd use 58. So that is the steel that we're using, how it's made, material properties, and our steel shapes that we're using, an overview of those. There's also 2 videos if you like to look at collapses, because that is often how we learn from our mistakes and how to be better structural engineers. Unfortunately, sometimes bad things happen when things collapse, but we always are learning something from it so that things are safer. So I have a collapse video on the World Trade Center from 2001. Which collapsed due to fire. Well, collapsed due to a plane running into it, but ultimately what happened was the fire weakened the steel columns. And then the I-35W bridge back in 2007 in Minneapolis, which didn't have any redundancies and collapsed from overuse. So those are some fun videos to watch, and that is our introduction to steel as a structural material. Thanks.